right, put cell phones, other distractions away. The thing about electron configurations, I always worry about people when they're gone today because they're going to come back and be like, what? But it's actually not that hard once you get it. It just sounds really weird and complicated to someone who has no idea what's going on. So with our electron configurations, let's talk about the 3 rules for our hotel. So when an electron comes to check into our hotel, rule number 1 is the Pauli exclusion principle. We introduced this last time, but this is the rule that says you cannot put the same electron on the same floor, in the same room, on the same bunk bed, and both on the bottom or both on the top. They will always be separate. Okay? So you can't do that. They need their own, right? So according to our 4 quantum numbers, so the principle is the energy level. If you want to add a note just to remind ourselves, this was the floor of the hotel. So 2 electrons can be on the same floor. That's fine. They can be in the same sub-level, which in our analogy was the room. The 2 electrons can be in the same room. The magnetic quantum number is the orbital, which in our case were the bunk beds. But then finally, the last designation narrows it down to a single electron, because that's telling us if it's on the top or the bottom of the bunk. Okay? And that has to be different. So with this idea of our electron configurations, we're also going to learn about these things called orbital diagrams. An orbital diagram is a visual representation of the electrons in the atom. Each orbital can only hold 2. So if you want to put a little like something next to orbital, remember orbital aka means bunk bed. Right? That's why the bunk bed can only hold 2. Whenever we use the word orbital, those are our bunk beds. Now there's a very particular way we have to draw them in there because one must be on the top and one must be in the bottom. So whenever you put arrows in the boxes, so the arrows these represent right here, so this represents our electrons, one must always be pointing up and one must always be pointing down. They will never be pointing in the same direction. So next to that box, let's draw a bad example so we don't do it. So draw another box next to this one. And point both the arrows in the same direction. And then put a big X on it so you know don't ever do that. Same thing, they both also won't spin down. That's what Pauli, so that's the first rule of our hotel. Okay? Second rule is something known as the Aufbau or Aufbau. If you speak German, you probably can say it better than me. But the Aufbau principle, this rule tells us that electrons fill in the lowest energy orbitals first. And this is where your map comes into play. Your map tells you the order that the hotel will fill every single time. Okay? Now, you always start at the 1s. So this right here is the beginning of your map every single time. And then the way that you read it is you read left to right and then down. So we start with the 1s room. Once the 1s room gets filled up, we then start putting electrons in the 2s room. Once the 2s room gets filled up, we then start putting them in the 2p room. Once the 2p room gets filled up, we then put them in the 3s room. Once the 3s room gets filled up, we then put them in the 3p room. So you read left to right and then down. Now this is where it gets a little weird with the numbers, because after the 3p, we go down to the 4s, but after the 4s comes the 3d. So be careful there with the numbers because we have some overlap of our levels. And the 3d overlaps with the 4, and so we get this shift. Now another really weird place is with this F down here. So I'm going to blow your minds here for a second and show you the way the periodic table should naturally look. We're used to it looking like so, right, or on your paper. But if we actually look, so everyone find cesium on your periodic table. So look at your ones with symbols. Find cesium. Someone shout out the number once they find it. 55, so find element 55, everybody. So if we count across, so read left to right, counting the numbers, it goes 55, 56, and then there's like this weird, like, on yours I think it's just like a gap, right? It has like a little star. So the whole section below, 57 through 71, should actually belong in that spot. So it should, let me pull this down so you can see a little bit better. If we go in number order, it should actually look, oh, that's not it, like this. I know, a little bizarre, right?
So why is it like, so why are they all organized in that way?
So like, why don't we put it like this all the time? Is that what you're saying?
Oh, I'm asking why are the rooms organized that way if it's like the rooms, like F is the 2 rows, why are they?
Because the F doesn't start coming until we start getting really big. Because there's not enough, because the F rooms holds 14 electrons, right? Or the S sublevel.
And why do none of the ones after that hold F?
Well, they do, we just don't have atoms big enough yet. So is there a 6F? Yes. It just doesn't, there's nothing big enough that will fill it up yet. Because the biggest element we have right now holds 118 electrons. And we don't need a 6F to fill it anything up past that. So, but if we keep making more elements, then it could one day get to that. So if you didn't already, I kind of drew it on mine, but I would make sure on your map that you draw an arrow to remind you to go down to the F. Because after we fill up, so after we fill up the 6S, you need to go down and fill up the 4F. And then after filling up the 4F, where would I go back to?
5D.
Back to 5D. So after 6S, so think of this whole thing, right, as getting squished in and that pushes over. So when you're reading your map, you have to go down and then back up. And that's probably one of the biggest mistakes is people just forget about the F completely and skip over it. But the nice thing is you'll start to recognize that the pattern is always the same. It always goes 1s to 2s to 2p to 3s to 3p to 4s to 3d and so on and so forth. Okay, and your map shows you that pattern. Okay. All right, so there's Aufbau's principle. Now, a note on our orbital diagram, so when we draw these boxes and arrows, each box represents one orbital. Once again, aka a bunk bed. So every box is a bunk bed. If it's one of our rooms that has multiple bunk beds, then you connect the boxes together. Okay, so for example, an S room has how many bunk beds? 2 electrons, so 1 bunk bed, right? So all S's are a single box because it can hold 2 arrows. But if you were drawing a p orbital, you draw 3 boxes all connected because it's one room, but there's 3 bunk beds in that room. So when they're separate rooms, don't connect them. But if it's just a bigger room, connect the boxes together.
Who came up with this? It's very confusing.
Stay with me, right? Remember the puzzle being put together today. Okay? And I don't know by name who discovered all this. A lot of people honestly have, because Pauli discovered the Pauli exclusion principle, Aufbau, you know what I mean? It's like a combination of lots of people. So.
Yeah, it's impossible.
Okay, we'll talk about why those arrows are that way here in a second with our last rule, but you can draw those in. Okay, so now the last rule that we have is known as Hund's rule. Oh, Just to review, up arrow we classify as +1/2. Down arrow we classify as -1/2 for the quantum numbers. So our final rule is known as Hund's rule. This rule tells us within a sublevel, you place one electron per orbital with their spins parallel before you pair them up. Okay? So the way I think about this rule, because it's kind of how life is in general for most people, right? There's exceptions to it in human cases. But you could think of if you were, so you and two friends are in a hotel room with 3 bunk beds, and there's 3 of you, what are you most likely going to pick for your sleeping arrangements? Everyone gets their own bunk bed, right? If there's an empty bunk bed, most people wouldn't choose to share with someone else. It's just like getting on a bus, right? If there's an open seat, normally you'll take that open seat and not share with someone else, okay? That's what Hund's rule is, and it's even more so because electrons are all negative. So they really don't want to share if they don't have to, okay? So according to Hund's rule, what we would never see is a situation like this one. So if we only had 4 electrons in that orbital, they're not going to leave an empty. That makes sense? They would rather be separate if they could. Okay, so fill in those arrows and then cross that off as that would never happen. But then what would happen is they would take their own, and then the first one, yeah, they do have to share because I've ran out of empty space. But if they don't have to share, they don't want to. Lizzie?
Will the ones that don't share always be up arrows?
Good. So that's, well, they tend not to be up, but they have to be the same direction. Okay. So that's the part right here where it says spin parallel. So let's actually draw another example that's wrong. So like above or below, or squeeze this in somewhere. So with what Lizzie was saying, something else you don't want to do, so draw your 3 boxes there. If I have 4 electrons, they would never do a situation, oh, let me back up too. You can technically, well, the real official way to do this is you actually just use half arrows. Now, if half arrows are weird to you, you can make them a full arrow. But you are allowed to use half arrows. In my opinion, it's actually easier. But just so you know, I'll typically do half arrows. So you would never see it like this, where these 2 aren't sharing and they're going in opposite directions. They both are up or they both are down. So that's what it means by spin parallel. So draw that and then put an X. That is incorrect. All right. Let's put this all together now, okay? So the goal now of what we're trying to achieve is when we have an atom, we are designating where the electrons are throughout the entire atom. That's what an electron configuration is it tells you the location of every individual electron in an atom. By knowing the location of electrons, it helps us to better understand the behavior of why atoms do what they do. So let's start with the simplest element on the whole table, hydrogen. So the first thing you want to do is figure out, you have the hydrogen there, is how many electrons are checking into the hydrogen hotel? Just one. So off to the right of this, or left, sorry, right, 1 electron. You got to know how many are checking in so we know how many people to put in certain places. Okay? Now, the question is, what is the first room we check electrons into? The 1s, right? So, for the configuration, we would write 1s. Now, how many electrons am I putting in this 1s room? Just 1. It can hold 2, but for hydrogen, there's just 1. So you're going to write 1s1. Make a note here that this number at the top tells us the number of electrons. Oh, I forgot a word there. Tells us the number of electrons in that orbital. So this is not a mathematical thing. We're not like taking it to the power of 1. This is a notation that tells you, hey, in the 1s orbital, there's 1 electron there. And for hydrogen, we're done, because that's all it has. Okay, so let's try lithium. Okay, so lithium has how many electrons in its hotel? 3. Remember, the atomic number is the number of electrons, because these are all
So
neutral.
is that how many it can only hold, or how many it has?
Both? Well, like, it could hold more. You can always hold more. Thanks, Jenna. But that's how many lithium naturally always has. So unless it's like bonded or something, it will just have 3. Does that answer your question? Okay. All right, what's the first room we put electrons in? The 1s room, right? So write 1s again. How many electrons am I putting in this? 2, because now I have 3 total, so we'll fill it up, right? Aufbau's rule says you fill it up before you move on. All right, what's the next room I go to? Good, so then we go to the 2s room. And how many will I put in this one? Because I only have 1 left. Good. Oh, I love that sound. Oh. I think some of you recognize, but if you didn't have that moment, the powers should add up to the total number of electrons. The powers only. Not the power and the number, just the powers. Yeah, Tyler.
Why did we skip over helium?
I don't know, I'm just doing examples. It would just take too long to do like all of them, right? I mean, the next one we're going to do is what? Sulfur, so no particular reason. Right? Is sulfur the next one?
Yeah.
Okay, so let's take a look at sulfur, everybody. So we got 16 electrons that all need a room. Okay, so where do we start? Okay. So how many can fit in there? 2. This is a new hotel. So each element is its own hotel, right? Okay, after the 1s gets filled, where do I go next? 2s. And how many can fit total in the 2s? Show me on your fingers what you think. Tyra, why is it just 2? It is 2.
It is?
Yeah.
Okay, so I thought it was just because that's the number of boxes in, or of rooms on the floor.
Because once again, this isn't like a math operation. What's the 2 in front telling us?
What floor?
The floor, but it's still an S room. And all S's only can hold 2 electrons. Right? It doesn't matter if we're on the 7th floor or the 1st. Right? Okay, very good. All right, where do I go after 2s? Oh, question.
I have a question. So like when you're doing this,
Yeah.
for the first one we did, is only 1 electron can fit in each box?
So when we draw the boxes, oh, those, yes.
So
yes.
like 1, 2?
Yes. Okay. All right, everyone okay so far? Okay, where do I go after 2s? Good. And if you're like, where are they pulling these from? We can find it on our map, right? We did 2s, so now we go to 2p. How many can 2p hold? 6, because p's have 3 bunk beds, so 6 electrons. Okay, after 2p, we then go down to 3s, which can hold? All right, so I've done 12 of my 16 electrons. So I got to keep going because I got 4 more that need somewhere to stay. So after 3s, come across to 3p. And it can hold 6, but how many do I have left? 4. Only 4. So 3p. So you read left to right on the map, right? So we did 3s, 3p. Got it? Okay, any other questions for now? More to come. But let's have you try with your table buddy. Go ahead and try nickel, and we'll see how we're doing. Okay, you got 2 minutes. Write out the electron configuration for nickel. Okay, ready? We're going to chant our electron configuration. Okay, so every time I drop my arm, you're going to say the next one. Ready? So ready and... Good.
2s2.
Good.
2p6.
Good.
3s2.
Good.
3p6.
Good.
4s2.
And
3d8.
good work. You guys have 3 smile bits. That was really nice. Good job. Questions so far? I thought I was going to trick you on the D one, but you guys did good. Okay, take a look. I guess 2 blanks. Let's fill those in on our notes. Okay, I'm going to skip a bunch of slides because that's just all the practice problems for people who are absent. Oh, first one if you didn't get, so a superscript should add up to the atomic number, right? And then we'll come back to these boxes here in a second. So keep in mind, and you already recognize this, I mean, I heard Gabe say it to Jordan, the pattern's always the same every single time, right? It doesn't change. So we will here in a second in case you're like, uh-oh, what if we have to do like Einsteinium that has 99 electrons? You literally do the same thing, but I will teach you a way you can abbreviate the long ones so you don't have to start at the top. But it is the same thing. That's the thing, is it's not harder to do the bigger ones. It shouldn't be harder, it's just longer.
Couldn't you just write the last one?
That's kind of where the abbreviation comes into play, yeah. Is it just focuses on the main end of it, not all the ones that are just filled out. The orbital diagrams that we're going to draw here in a second show us the same information, but in a visual way. That's it. Okay, so if you can do what we just did, the orbital diagrams are just a picture of that. Not different in like solving it, just a picture. Okay, so take a look at silicon there at the bottom. And let's have you, we'll have you guys, since you guys are good at practicing, let's have you do silicon and what's the one next to it? Calcium. So I'll give you 2 minutes to do silicon and calcium with your table buddy real quick, and then I'll show you how to do the boxes. Questions? Anyone's not matched and they don't know why? Okay, underneath silicon on your paper, let's now draw what's called the orbital diagram. So this is called the electron configuration. The orbital diagram is now we're going to draw the boxes and arrows that represent the same thing. So for the 1s orbital, that's 1 orbital, so draw 1 box. Label the box as 1s. How many electrons are in this orbital? 2, and how should the arrows be positioned?
Up and down.
Good, opposite way, so point 1 up, put 1 down. So this is a picture of what that says. Okay? Now, it's important to recognize this is the 2s, so it should not be connected because it's a separate room. So the 2s is just next to it. Same thing, up, down. Now, the 2p orbital is how many boxes? 3, and they should be connected because it's the same sublevel. So 3 boxes all connected for the 2p. Now it's all filled up, so just put the 6 in there. Not that many boxes, but maybe later. So 3s is going to be how many boxes? 1 box. Once again, separate from the others. Electrons go up, down. Now for the 3p, it only has 2 electrons, but you have to draw it to its true size. So you still draw all 3 boxes.
How do you know if the arrows are pointing up or pointing down first?
Are you talking about like for this 3p?
Yeah.
So we only have 2. So first off, do they share a box?
No.
No. And then besides that, it actually doesn't matter, Tyler. They just have to be the same way. I always go up first, up, up, but you could have gone down, down. Doesn't actually matter. So, questions on orbital diagrams? Want to ask for that? Good? Okay. Question, Asmin?
Yeah, so why do you have to draw the 3 boxes?
because that's the size of the 3p. Because it could hold 6, right? So you have to show even the empty ones if they're there. So even if, like, when we start drawing the D's, right? Even if you only have 1 electron in a D, you still draw 5 boxes because that's how big it is. Does that make sense?
Yeah.
No, good clarification. Bryn?
So you had like 4.
Yeah.
Would you like fill all of them up like by themselves and then you like it down your
Yep. So you always fill them up individually. So it'd be up, 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 and then go back and go down. Okay, so our next thing here that I want you to recognize, and some have already caught on to this. So my daughter right now, who's gonna turn, she's not quite 2, she'll be 2 this summer. Her new favorite thing is to like say wow. Like little kids get amazed by this silliest little things, right? Like bubbles are like her new favorite things, and like she'll just the whole time like pop it and be like, wow, wow, like for like hours every day. But it's so fun to see it, right? So this is your moment, I hope, where if you haven't made this connection yet, you can have that wow, because it's really cool. So look at this, everyone. Okay, so here's our electron configuration for silicon, sorry. Another connection to the periodic table can go like this. So we said 1s2, so 1s2, 2s2, 2p6, 3s2, 3p2, and what is this square on the real periodic table? It's the one I'm trying to write. So you don't actually, like some people were like trying to keep track of the math as they went. You actually don't have to do that if you just know where you're stopping. Right, so if you just go to your map and you say, okay, I want to stop here.
So that's the shortcut?
No, there's actually a better shortcut.
Whoa.
Yes. So if you think that's good, just wait. Okay. Questions? Okay, let's take a look now at the real shortcut. So sulfur's normal configuration, if you look at the top of page 5, I gave you sulfur's configuration already. 1s2, 2s2, 2p6, 3s2, 3p4. The way that we can do these shortcuts or the abbreviated form is pretty much scientists recognize that the only electrons that matter in reactions are the valence electrons, just the ones on the outside. That's really all we ever care about. Like when we do charges and things, it's just the valence. And so all of those other electrons that are in these rooms and orbitals, yeah, that's great, but it doesn't mean anything to us. So the abbreviated form kind of just groups them all together. So if I wanted to write a shortcut for sulfur, the rule is you find the nearest noble gas that is lower in atomic number. Now, who remembers where our noble gases are?
It's on the very far right.
Yeah, so very, very far right, column 18. These are the noble gases. Recognize, because some of you are getting this mixed up, the other red ones are gases, but they're not noble. Just this column. And these two aren't part of that family. Okay? So if I want to shortcut sulfur, the nearest one that's lower in number would be Ne, neon. So what I would do, so write this down on the abbreviated line. So I would put Ne in brackets. And what's the atomic number for neon? 10. So this little box takes care of 10 of my electrons. I don't have to do anything with them, and we can just start on the next spot.
Which is S.
So all of this is filled, so I start now at 3s. So we just do 3s2, 3p, what do you need sulfur? 4. And now you're done.
Oh my gosh. Why didn't you just teach us that?
That's what people always say, but it's like, you don't understand the shortcut, you know what I mean?
Isn't there even bigger?
And you wouldn't appreciate it.
Can't you get a shorter shortcut if you just write the final symbol in? Because it's 3p4, then that would just mean you go to 3p in the form symbol.
So the thing you have to remember, and the reason why we can use the noble gases, right, is the whole point of these configurations is to give us information about the electrons in the atom, right? And the ones that matter are all the ones on the outside shell, and all of these are on the outside shell. So we don't want to like hide them away, because in later things when we start using these configurations, seeing them gives us information. It's kind of like, sorry for those that maybe thought this. So if I told you, hey, I want you to write the electron configuration for krypton, Kr, you can't just put Kr in brackets and be done. Sorry. But you could put Ar in brackets and then just do the row after. Because we're trying to get information, and if you simply just write something in brackets, that doesn't tell me anything. Okay? All right, let's have you try the next two. I think it's like, what are the two below? So do the shortcut for germanium and chlorine. Okay? So try the shortcut method with germanium and chlorine. Okay, check your answers with mine once you got them. And then for final check, because if you can do this one, you can do any of them on the homework. Not quite, but really close. So for 4 smiley faces, I want you to write the electron configuration for Livermorium.
You did not.
Okay.
Just lied.
And yes, you can please use the shortcut.
Oh wait, yeah.
It's number 116.
Do we have to do that? We did it already though. Oh. No, it's not.
Good? Awesome. I haven't given out very many days. So wait. Okay, anyone miss it or have a question about any of these things? Aubrey? Yeah. So yeah, if we wanted to draw, so if it said draw the orbital diagram, you could pretty much same thing. You'd write RN to say, hey, I'm shortcutting, and then you'd only draw the boxes for the ones that follow. So, good question. Any other questions? Okay, now there's, on your homework assignment, this is the last time I'm gonna not totally let you use the shortcut every time. After this assignment, you can use a shortcut every time, even if you want to shortcut lithium. It's kind of lazy, but actually, I don't know if it's lazy, it's just the same length in my opinion. But you can do it if you want, okay? But for the homework assignment, so it's the one that says electron configurations, the front page, and none of them are too big, but just to get us in the pattern of it, the front page, you can't, I don't want the shortcut yet. But after that front page, you can always do the shortcut every single time.
All right.
Okay?
So the front page, not allowed.
Front page, no, but please on the back side use the shortcuts because those are the ones that get big. I have posted these answers on my website, so double check. You can make sure you're doing it correctly. We're just going to work on the homework until the bell rings.